So now let's imagine that there was an infinitely large but uniform sheet of current. This gets away from the typical current through a wire, right, which kind of is one dimensional, but we've seen examples of where wires are two dimensional. Now we are really in the two dimensional regime. So let's draw an axis, and then we will place this sheet on this axis such that it kind of looks like this. Let's do all right, and so the squiggles are to kind of tell you that it's an infinite sheet, right? It's not of uniform or a constant area, right? It's uniformly big. Let's say the current direction goes in the plus x direction, okay? Plus x, so towards us. How do we find the magnetic field around this region, right? Which direction does it point? Well, if that's the current, like always, we use the right-hand rule and put our thumb in the direction of I, and then our fingers will curl in the direction of the magnetic field, right? So let me rotate this diagram a little bit, and if I were to down below here, that's a little too far. If I were to down below here, that's the y-axis, z-axis, I'm going to write this sheet such that there are charges now, or you can imagine an infinitely dense packet of wires, right? And because the current is coming in the x direction, it's coming towards us. So I'm drawing a lot of wires with dots on them. Okay, that looks all right. Maybe one more. Okay, so what's effectively happening is, well, if your thumb is in the direction of current, so towards us, out of the screen, let's choose one. Let's choose this one here. That means the magnetic field will go like this, right? Like that. And a little bit further away, it'll go like this, right? Keeping a constant distance, a constant radius, and even like this. Okay? So that's for this wire right here, right? Or that part of the sheet. The same thing can be true for a wire on the exact other side, right? In the minus y direction, on the other side of the z-axis. So that was 1, 2, 3 wires away. Let's go 1, 2, 3. So now, same thing occurs over there, right? It curls in the counterclockwise direction. I don't think they're, well, they're close. Okay? And what actually happens when you have multiple lines or multiple parts of this sheet is that at some places the magnetic field is going up, where in other parts it's going down, right? And case in point is for right there and right there. For the part of the sheet on the left, the magnetic field is going up, like that, right? From the part of the sheet on the right, that field is going down. So right at this intersection, they cancel out, right? Same thing for up here. I haven't really drawn it exactly to scale, but that effectively happens in this interim, right? In between. And so that happens for that section and that section. Well, the ones that are 2 away, the ones that are 1 away. It happens for every combination, every part of that sheet. They cancel out. Some parts are going up when other parts are coming down. And so what effectively happens is that there is an overall direction to the magnetic field. Notice above, both parts or all parts of the magnetic field generally point that direction. below the surface, they generally point this direction, right? In plus y. And so that's important for this uniform infinite sheet of charge. Up and down in the z direction, they cancel out at all points. For all y values and all x values, they cancel out. But they do not cancel out for all z values, right? The heights, in other words. So now let's use Ampere's law to determine the magnitude of the magnetic field. All right. So we need to draw an Amperian loop such that the current passes through the Amperian loop, right? I don't want to draw it parallel, right, to that current. I don't want to do that because then the current will just pass along it and skim along. I want to draw it such that the current is perpendicular to the face of this Amperian loop. So what I will do is this. And I'll actually reverse my dotted line and solid line convention to try and show you what's above and below this sheet. But that is our Amperian loop. And we can draw it of length, whatever we want. I'll call it length script L, right? The height, it'll turn out that it does not matter, okay? So it's of length, or I'll say the y width of script L. And so we need to evaluate all sections, all parts, for 1, 2, 3, and 4, right along the bottom, okay? And because we have some above and below, we're going to have to multiply by 2, effectively, right? So what do we have? The DS's for all parts in section 1, the DS we can say is going up. So that DS is actually perpendicular to the magnetic field direction, which from my diagram below, magnetic field was going in the minus y hat direction, and below it's going in the plus y hat direction. So therefore, in section 1 here, ds is going in the plus z direction. So that's perpendicular. That does not contribute. Section 2, ds is going in the negative y direction, and that's parallel to b, so that does contribute. So, whoops, still in blue. We have integral b ds cosine of 0 now. That's segment 2. Adding that with, can you guess? Segment 4 along the bottom, right? The ds here along the bottom. The ds vector points in the plus y direction, parallel to b because it's below now. Sorry, we're dealing with that magnetic field, since we are below, is parallel with that ds along the bottom. So I suppose I should make the 4 specifically for the bottom round. That's also 0. And that, of course, equals mu naught I enclosed. What's the I enclosed? I could just say I, but this is a sheet, right? It's a sheet. Typically, we don't talk about it in terms of current. We talk about it in terms of current density, J, which is related to the current simply by I over some area, or in this case, length, right? It's a current density, I over L. And so that's equal to, where is it? J times L, okay? And so the left side of our integral is fairly straightforward. The integral ds, well, that's just L. BL, we're adding plus BL there. And that's equal to mu naught J times L. guess what? The L's cancel, and we have 2b, which turns out to mu naught times the current density over 2. That's the magnitude, and the direction depends on, well, where you are, right? If you're, let's see, if you are, it's minus y hat for z values greater than 0. And why am I writing that so far over there? I have plenty of room. Magnetic field is negative mu naught j over 2 in the y direction for values above the sheet, which effectively means z greater than 0. And it is positive mu naught j over 2 in the y hat direction for values of z less than 0. Okay. So hopefully this gives you a little bit of insight into how to deal with a two-dimensional surface that's not simply a wire, right? So this is our magnetic field above and below an infinite sheet of uniform current.